Well, hello, everybody. My name is Giannis Daras, and my experience with Explosion AI people in Spacey started 1 year ago when I got the Google Summer of Code project for adding Greek language to Spacey. And after that was over, Matt and Ines said to me, like, you can work with us. And that was a great opportunity, actually, because the last months I'm here at Explosion AI, and I think that we are doing some really cool stuff that I'm really honored to be able to share with you today. So, to give you a brief overview of what we are trying to do, Sebastian before said that, OK, we are having like powerful transformers models, and that's cool. We are having BERT, and the whole world has gone BERT crazy. But the thing is that BERT isn't accessible to anyone. And BERT isn't accessible to anyone because it's a very large model, which requires really hard pre-training, and that takes days and really costs a lot of money. And it's also too slow, and sometimes too slow to use for production. So today, I'm going to show you some really recent unpublished research work that I've been doing in order to create a variation of BERT which is much faster and which can run without having like a factory of GPUs, which obviously is a good thing. So first of all, let's take a step back and say, why do we need transformers? We have feed-forward neural networks, we have recurrent neural networks, and we have GANs, or I don't know, fancy architectures. So there are some problems with these approaches. First of all, feed-forward neural networks don't take advantage of the fact that a sentence consists of words, and it just like packs the world all together. So that's a problem. And then we have recurrent neural networks, which are good, but if you need to pass a sentence, you need to pass it token by token to take advantage of this recursion, which makes them sometimes slow, and also sometimes they fail to understand long-term dependencies. And also we have some other fancy neural nets that don't apply to NLP. So here is the transformer architecture. I'm not going to spend a lot of time here. It's just like an encoder with encoder layers and a decoder with decoder layers. And today we'll be talking mostly about BERT. We just kept the transformer encoder from this architecture. So first of all, what are the benefits of using transformers? Well, obviously, there are a lot of benefits. The first one is that we have achieved state-of-the-art results in many tasks, and that's really what matters, after all. And they have been able to model long-term dependencies, and they are doing well. And also, they do that in single pass. So we need to look at that and say, OK, that's amazing. How do they do that in single pass, contradictory to recurrent neural networks? And the secret is the attention layer that they are using. And I'm going to focus on the attention layer because the variation of BERT I'm proposing, it mostly changes the attention layer and does the whole BERT run much faster without sacrificing performance. So if we need to explain attention in simple words, we would say that attention is a way to get vector representations for a word, but a word in context. So that's really important. And yesterday I was having dinner at a restaurant, and there was this guy, Vincent, who said this, which I would like to quote: "What lies in word embeddings?" And that's a really good example of why do we need contextualized word embeddings, because the word lies has two meanings, obviously. And if we want to represent this sentence as a vector, we need to understand the context on which word lies is used. So we can have a word embedding that uses this context. So to do that, BERT uses the attention layer, which is basically this figure we are showing here. And I'm going to split that for you in single words. So I'm making sure everybody's on the same page. And then we will move to variations of it that are much faster. Basically, there are three matrices that are associated with the attention. And the first matrix is the query matrix. And the query matrix is actually who is asking? What is the vector representation of the word that is asking for having a representation in context? So we can think of query matrix as who is asking, and then we can have the key matrix, who is actually who are we asking to? We are a word, and we want to change our representation and to get a better representation in context, and we are asking other words, other surrounding words for that. So that's the key matrix, the matrix that has vector representations associated with those words. And if you multiply the query matrix with the transpose of the key matrix, and you normalize that, and you are taking a softmax, then you end up with the attention matrix, which is actually a matrix with n times n dimensions. And at its position, let's say at cell I, j, we have how important is the context of j for the context of the token at position j for the token at position I. And that's really important. It means if we skip j, do we lose a lot of information about I? How important is the relation? And that's the secret of BERT. That's how it works. And the values matrix, it's a way to get back from like this representation to the model representation to feed forward in the next layers of the network. So, and obviously, sometimes we do that in heads, which means that we have separate values, keys, and queries matrix, and we can cut them. But that's not so important, so let's keep it. And if you need a quick visualization of the attention, it's like this. We can see there that we are asking about the word the to find the contextual representation of this word. And we can see that there is a query vector associated with the, because this is the token that asks for information from the surrounding tokens. And it's asking all the keys. And if you get that product and the softmax, then you can see that some words are more important for the than others. So we have an example of 2 sentences, and at this example, the only takes the representation from the first sentence. So that's how attention works. But if attention is so ideal, what's the problem with it? Well, actually, there is a really important underlying problem, and the problem is that attention has quadratic complexity, and has quadratic complexity in terms of memory and in terms of time. That actually means that if you have like if you had a model like a recurrent neural net or something like that, then you need quadratic much more memory to run the same task if you are using transformers. And that makes transformers really not accessible to people. And if we're talking about democratizing the AI, that's not the way to do this, because not all have like factories of GPUs. So we need a way to change that and to make it more accessible to people and to make it faster. So OpenAI did some really good work on introducing a way of dealing with that problem. So they proposed attending in steps. That actually means that if token A attends to token B, and before that, token B has attended to token C, then A has information of token C and doesn't need to attend all the way from the beginning. So we don't need to attend to all the tokens and to have a quadratic complexity, because we can take advantage of this method, which is called closure, like attention is an attention factorization using this property, the closure property. And for doing that, they introduced 2 patterns. And I'm going to focus on the first pattern first. Let's see what we are seeing there. First of all, we are seeing a sentence with 16 tokens, and each token is numbered in this sentence. And in this figure, we have with the dark blue the position, the tokens that we attend to both steps. We are talking with about 2 steps attention, and the dark blue is the positions that we are attending to both steps. And the light blue is the positions we are attending to the first step, and the green is the positions we attend to the second step. So let's see, for example, token 6. Token 6 at the first step, I mean the light blue color, attends to 5, 4, and 3. But in the second step, attends to 6, 5, and 4. But in the second step, attends to 3, which has already attended to the previous tokens. So in this way, we can say that token 6 still can see all the left context of this representation, still can have access to all the left tokens, but we are not like using all the positions in this matrix. We are using a very small subset of them. And if you're wondering how small is this subset, the complexity of this is n root n times root n. So, yeah, OK, they created this pattern, and they didn't go really well for NLP, but it did great for images. So they proposed another pattern, which is the fixed pattern we are showing here. The same logic applies for the colors. And there's no point like spending too much time on seeing what's happening, but believe me that each token can attend still to all the left context of it. And this went really, really well in NLP task. And what I mean by well is that it achieved like low perplexities in a Wikitext dataset that it was trained on. So OpenAI proposed those patterns, but there are some serious problems that I think that we need to consider. The first thing is that they didn't tell us how to choose those patterns, and they didn't tell us, like, if we design such patterns, do we know beforehand which patterns are going to work or not? And the second thing is that they are not bidirectional. Sebastian mentioned that before, that it's really important in the pre-training to have bidirectionality, because you get more powerful representation. So those patterns are not bidirectional, and we need to tackle this problem. But in order to tackle this problem more generally and to find a systematical way of proposing such patterns, we introduced the concept of information flow graphs. So what information flow graphs are? Information flow graphs simply show how information flows in the sparse attention steps. So I think it's better to explain it with a visual. And we are going to see how the information flow graph for the strided pattern we saw earlier looks like. So it looks like that. And let's consider that we have at the first column the initial tokens, and at the last column we have the final tokens. And let's see the first token at the last column. This token only attends to itself, because the patterns OpenAI proposed are patterns that are looking at the left context and are not bidirectional. And we are losing information from that, actually. And the same applies to the fixed pattern as well. And we can see how it looks like here. It's the summarization I was talking about before. But again, we can see that the same problem is here. So yeah, we are losing information. And basically, we are losing information because the patterns are not bidirectional. And in this work, we propose bidirectional patterns. And also, we consider constraints that everybody should have them in mind when designing information flow graphs, because in that way, we have a systematical way of designing, and we know beforehand, before running the experiments, which patterns are going to work and which not. So the first thing is that we don't want to have a high complexity, and that means that we don't need a lot of edges in the graph. Dense attention uses n² edges, and OpenAI uses n times root n edges, but they don't have bidirectionality. There is a formal proof that we have done, and it's pretty easy, actually. You can do it for home, like. And we have proved that if you have a fixed in degree, meaning that a fixed number of arcs comes inside each token, then you can't go lower than that for bidirectional patterns. And we propose such patterns that that are reaching this lower bound. So from that perspective, we are optimal. Yeah, but we said that we need a fixed in degree. Who says that? I mean, maybe we don't need a fixed in degree. Maybe we can just do random things. And actually, that fixed in degree actually implicates something really, really interesting. Because let's look at this information flow graph. Clearly, every token here has full information. It can see any other token. At the final step, we can see any other token. But does this feel right? I mean, I'm pretty sure that this is going to fail in the experiments, because we have a really bottleneck token summarizing all the information of the sentence, and there is a lot of compression going on there. So this is going to fail. So we propose in degree as a way, or a constant in degree as a way to fix that flow problem. And a more generic approach would be like to see how much flow comes from the input of the graph to the output of the graph, only allowing its token to output flow 1. So if you're designing a new sparse pattern which seems really cool, you can count these and see if a lot of flow comes from input to the output, that basically means that you have designed a good pattern. And if not, that basically means that you are doing something wrong, because you are compressing so much, the network cannot cannot fit in a so small space, the summarization that goes there. So it's too much compression. So we consider two natural extensions of the fixed patterns that OpenAI proposed. And actually, I'm saying that they're really natural because we just added the missing parts. So we have the optimal thing without using too much edges. So that's the first one, which is called left-to-right full information sparse attention pattern. But we also have the right-to-left full information sparse attention pattern. And that goes us back to the idea of going from left to right or right to left. We are losing bidirectionality. Here we have bidirectionality, and also we have two ways of achieving it, which is kind of important. And yeah, this is how the information flow graph looks like. And believe me, if you go and notice there, that you will find out that every token can attend to any other token, and we are only using n root n token. So the complexity of this, the time and memory complexity of this is much better, and it suits the problem. We pre-trained on that. We pre-trained those sparse transformers, and we got really cool results. They are still preliminary, but we are achieving over 92% on IMDb. So I think that we are having something here. We still need to examine it more thoroughly, but that seems to work, and I think that it's something that we should pay attention. And a last thing that I would like to mention before my talk finishes is I mentioned that we do attention in steps, but I didn't tell you why, because the simple attention is straightforward, the dense attention. And actually, it turns out that there are 3 ways of attending in steps. And the first way is what we call Intellive mode, Intellive attention mode, which means that the first layer uses the first mask, the first pattern, the second layer uses the second pattern, and so on. And because there's a time, the time axis there, you have this property of closure, but this only works if you have a stack of layers. It's OK if you don't understand all the details here, but I'm just going to give you a brief idea. And also, we can use a merge head, meaning all the masks at one step, which is basically the figure here. And last but not least, this is the way that it turned out to work really, really well in experiments, which means that basically different heads attend to different things. And if you concat them, you still have full information, you have this closure property, but you also allow the model to explore different patterns at the same time, which is really meaningful. And I think that there is some research that needs to be done here, why this works and why maybe something else doesn't work. But yeah, still, this went well in experiments, so that matters. Yeah, and that's all. And if there is something that you should remember from this talk is that obviously transformer models are too big for industrial NLP frameworks such as Spacey, and are too expensive too for people. And if you're a company or something that you want to run some fancy NLP stuff, I think that it's really painful to have like a server having a 24 layers BERT, which is too slow and consumes too much memory. But sparse transformers could be a good alternative to that, because they need much less memory, and they can run much faster. And I think that's an ideal fit for Spacey, because Spacey is the best framework I'm aware of in Python for NLP. And actually, its power comes from its speed. And I think that sparse transformer is on this direction. And you don't like having a really big running overhead if you use those instead of convolutional LEDs, for example. And actually, I think that this could be also really important for the recent command that Spacey uses, which is the pre-train command. I was at the training yesterday and the day before, and some people say that is really cool, but it's too slow, and maybe we don't get the best results out of it. I think that using sparse transformers and the pre-training objective that was designed for transformers would give like a big benefit to Spacey, and we are working on making this accessible to people. So that's all. One thing before I finish is that this is a joint work with Alex Dimakis from Austin, Texas, which is my supervisor from there, Alex Potamianos, which is a supervisor at NTUA, and Georgios Kivopoulos, who is a friend of mine. So thank you very much. I hope you like my talk.